The video will start in 5, 4, 3, 2, 1.
The stellar-driven universe, a comprehensive theory of universal expansion, galactic formation, and temporal dynamics abstract. This theory introduces a revolutionary approach to cosmology, proposing that the universe's expansion and galactic formation can be explained by observable stellar phenomena rather than dark matter and dark energy. Specifically, it suggests that the combined forces of solar winds and the remnants of population 3 stars are sufficient to account for cosmic expansion and galactic cohesion. Additionally, this theory redefines time as an emergent phenomenon influenced by relative motion rather than a fundamental constant. By grounding cosmological models in measurable forces, the stellar-driven universe offers a unified, empirically testable, and philosophically profound framework for understanding the cosmos. This profound philosophical depth stimulates intellectual engagement and curiosity, inviting further exploration and debate. Introduction: Rethinking the universe. Current cosmological models rely heavily on dark matter and energy, hypothetical constructs that explain otherwise unexplained phenomena. Dark energy is postulated to drive the universe's accelerating expansion, while dark matter is thought to provide the missing mass required to explain the gravitational behavior of galaxies. However, while widely accepted, these concepts lack direct observational evidence and remain theoretical. The stellar-driven universe theory challenges the necessity of dark matter and dark energy by proposing that the universe's large-scale dynamics can be explained through natural processes associated with stars. By focusing on forces that can be directly observed and measured, such as solar winds, magnetic fields, stellar rotation, and gravitational effects from black holes, this theory offers a simpler and more grounded alternative for explaining the structure and behavior of the cosmos. This grounded approach instills a sense of reassurance and confidence in its validity, providing a solid foundation for further exploration and discussion. Part 1. The challenge of current cosmology. The theories of dark matter and dark energy, while widely accepted, have emerged from observations that current models struggle to explain. Dark matter is believed to be responsible for the gravitational glue holding galaxies together, while dark energy is thought to counteract gravity, driving the universe's accelerated expansion. Despite extensive research and numerous experiments, these theoretical forces have yet to be directly detected, leading some to question whether they are necessary. The stellar-driven universe theory aims to address these cosmological challenges by proposing an alternative model rooted in observable phenomena, such as stellar activity, gravitational effects from black holes, and cosmic magnetic fields. This theory aims to address these cosmological challenges without relying on speculative forces or particles by proposing an alternative model rooted in observable phenomena. This stellar-driven universe model posits that stellar activity, combined with gravitational effects from black holes and cosmic magnetic fields, provides a sufficient framework to explain cosmic expansion and galactic structure. Part 2. Universal expansion via solar winds. The concept of solar winds as an expansive force. Stars continuously emit charged particles, known as solar winds. The force of these emissions may seem negligible. However, the cumulative effect generates an outward pressure that could drive universal expansion across countless stars and billions of galaxies. Rather than relying on dark energy, this theory suggests that the combined force of stellar solar winds could push galaxies apart, producing the observed acceleration in the universe's expansion. Types and intensities of solar winds. Different types of stars emit solar winds at varying intensities. Massive stars, such as supergiants, emit stronger winds than smaller stars, and this variability in solar wind strength contributes to local differences in expansion rates. Galaxies with denser star populations emit more solar wind, potentially causing accelerated separation rates in some universe areas. Impact of stellar life cycles on expansion rates. As stars evolve and eventually die, they release vast amounts of energy through supernova explosions. These events contribute significant outward pressure, further fueling cosmic expansion. This dynamic change in stellar wind output across different life stages of stars might explain the varying rates of expansion observed over cosmic time. Part 3. Cosmic magnetic fields as an expansive force. The role of cosmic magnetism in expansion. Solar winds are accompanied by magnetic fields that interact with the magnetic fields of other stars and interstellar space. This magnetic interaction enhances the repulsive force between galaxies, providing a natural mechanism for accelerated expansion. Cosmic magnetic fields act as a multiplier, amplifying the effect of solar winds and contributing to the large-scale expansion of the universe. Observational evidence of cosmic magnetism. Galactic clusters often exhibit detectable magnetic fields, which could align with the stellar-driven universe's predictions. By acting as a medium that strengthens the effect of stellar winds, cosmic magnetism provides an observable mechanism for universal expansion, supporting this theory over dark energy models. Part 4. Population 3. Stars as the seeds of galactic formation. Formation of primordial black holes. Population 3 stars, the first generation, were massive and short-lived. Upon reaching the end of their lives, these stars went supernova, leaving behind black holes that became gravitational anchors for future galaxies. In this theory, these black holes serve as the seeds for galaxies, gathering surrounding gas and matter and creating galactic centers. Black hole seeds without dark matter. In traditional models, dark matter is hypothesized to stabilize galaxies. However, the stellar-driven universe suggests that these supermassive black holes can anchor galaxies, making dark matter unnecessary for explaining galactic cohesion. This natural gravitational center, created by population 3 black holes, offers a grounded explanation for galaxy formation and stability. Implications for galactic cohesion. Galactic cohesion is achieved through the gravitational pull of these black holes, complemented by observable matter within galaxies. This approach aligns with the presence of supermassive black holes at galactic centers, supporting the idea that they play a foundational role in holding galaxies together. Part 5. Galactic shape. Determined by primordial star rotation. Rotational dynamics of population 3. 3 stars. The rotational speed of population 3 stars during their collapse likely influenced the shape of their resulting galaxies. Faster rotation leads to more incredible angular momentum, which can result in a disk-like structure typical of spiral galaxies. Slower rotation produces more isotropic distributions, forming elliptical galaxies, predicting galactic morphology based on stellar rotation. This theory proposes that galactic shapes, spiral, elliptical, and irregular, are determined by the rotational properties of population 3 stars. Observing correlations between the rotation rates of modern galaxies and their shapes could validate this model, providing an alternative to dark matter explanations for galactic morphology. Part 6. Time as an emergent phenomenon, linked to motion-time perception, relative to motion. Traditionally, time is seen as a constant that progresses independently of an object's movement. This theory, however, proposes that time is experienced differently based on relative motion. An object at zero velocity relative to the universe may perceive time instantaneously or not at all, suggesting that time is not an absolute constant, but an emergent property influenced by movement. Quantum implications of zero velocity. Achieving zero velocity relative to the universe could lead to unique quantum behaviors, potentially collapsing uncertainties in time perception. This theory suggests a link between quantum mechanics and time as an emergent phenomenon tied to cosmic motion. Experimental and observational proposals. Testing this idea could involve studying time dilation effects near black holes or attempting to measure time at different states of cosmic motion. Observing these effects could provide valuable insights into the nature of time and its relationship with motion, supporting the stellar-driven universe's alternative view of temporality. Part 7. Observational tests and future predictions. Galactic motion data as evidence. This theory can be tested by analyzing galactic separation rates relative to stellar density, using datasets from observatories like the Hubble Space Telescope and the James Webb Space Telescope. Observations showing that galaxies with denser star populations exhibit accelerated expansion would support the stellar-driven universe model. Local galaxy comparisons. Observing interactions within the local group, including galaxies like Andromeda and the Milky Way, could reveal patterns consistent with solar wind-driven expansion. We might gain further insights into the forces influencing galactic separation by studying localized interactions. Part 8. Addressing counter-arguments and challenges. Solar wind accumulation over cosmic distances. Some may question whether solar winds are strong enough to drive separation across vast distances. However, the cumulative effect of these forces, akin to small tidal forces generating substantial ocean movements, may influence galaxies' expansion over cosmic scales. The role of black hole. Anchors in galaxy formation. While critics may question if black holes alone can account for galaxy formation, this theory emphasizes the role of angular momentum and accretion dynamics in creating stable, diverse galactic structures without requiring dark matter. Part 9. Philosophical implications of the stellar-driven universe. Cosmic connection to human perception of time and movement. If time is relative to cosmic motion, our perception of reality may be shaped by our position in the universe. This theory challenges us to reconsider time not as an absolute constant, but as a dynamic experiential property tied to movement within the cosmic framework. The universe as a living system. Viewing the universe as a dynamic, interconnected system shaped by stellar processes gives us a perspective where the cosmos operates as a living entity. This view aligns with philosophical interpretations of the universe as a self-organizing, evolving structure fueled by the life cycles of stars and galaxies. Conclusion. A new paradigm in cosmology. The stellar-driven universe offers a grounded alternative to dark matter and dark energy models by focusing on tangible, measurable forces like solar winds, magnetic fields, and stellar dynamics. This theory challenges traditional cosmology and redefines time as an emergent, relative experience influenced by cosmic motion. It opens new avenues for scientific research, philosophical inquiry, and understanding of our place in the cosmos. With this model, we are invited to explore the universe not as a static system, but as a dynamic, evolving entity driven by forces we can observe and understand.
And thanks for watching.